Welcome everyone to today's video. We're going to talk about the kinetics of polymerization reactions. Okay. So a polymerization reaction is just some type of chain reaction, right? Where a chain reaction is something that once it gets started, it kind of sustains itself, right? And it keeps itself going and going and going and going, right? And in polymerization reactions, what's happening is you have reactions between different monomers that link up more and more and more to form larger and larger polymers, right? As the reaction's going, the polymer sizes increase, the molecular weight of your polymers will increase over time, right? And so we'll talk a little bit about the kinetics of these things and how we can describe the weight and size of polymers as a function of time, right? You know, so if you're doing a polymerization reaction, right, you want to form polymers of certain molecular weight, certain size, right? You might have an idea of roughly how long must that reaction run to get that, to get to that point, for example, right? And so there are two types of polymerization reactions. There's stepwise and chain polymerization reactions. We're going to focus mainly just on the stepwise here in this class and in this video. Okay. So for the stepwise polymerization reactions, right, it works in which you assume you have kind of a solution, if you will, of monomers, right? And basically for stepwise polymerization reactions, any monomer can react with another monomer to start linking up to form polymers. And links of monomers, okay, you know, can link up with each other to form larger polymers, right? So this linked group of monomers here, right, could react and link up with that. Now, it's not going to react in the middle here, right? It's going to be this end piece react with this end piece to form a larger polymer, right? But any monomers can interact with other monomers, right? But once they're, you know, but when they're, say, linked and say this guy here, right, this guy's not linking up or things like that, right? The idea is you're forming a linear chain of these polymers, okay? Right, and so in this case, right, you have multiple small polymers forming at the same time in your solution, right? And it's not that you have just like one polymer that's slowly increasing over time, okay? So an example of this type of polymerization reaction is the formation of nylon 66, right? So the monomer reaction kind of given here to form a dimer, right? So this product here is just a dimer, right? You know, and how this works, right, is you have an NH2 group and then CHOOH, right? And those react, right? NH3 plus, you know, CH2 or 3COOH, right? Will form, right? You know, water, and then, oh, well, this is just acid-base reaction. I'm writing out this reaction poorly, right? But basically, right, the idea is this nitrogen end will react with the carbon end, right? And what will happen is you'll form a nitrogen-carbon bond, right, and kick off a water, right? And so this thing gets linked up through this nitrogen carbon bond here, right? And then you know, each end can still react with something else, right? You have a lone hydrogen and a lone OH group sort of at the ends of this dimer that can then react with another monomer to form a trimer and so on and so forth, right? This is a condensation reaction, okay? And it's called a condensation reaction because it formed water as a product. So for this reaction, we're going to call the monomers just A. We're going to say A, right? And so the rate law for this reaction, right, is as follows, right? The rate of the reaction, which is related with the change in concentration A, is a function of time, right? Or negative of that, right? Is going to be minus Kr A squared, right? Where Kr is some rate constant for this polymerization reaction, right? And it's a second order reaction, right? Because you need a monomer and a monomer to collide to react, right? So this is the thing, overall second order, right? And so that's the rate law for this reaction, right? Which has an integrated rate law, right? For just any old second order reaction given there, okay? Now, And so that's good, so we can have an idea of what's the concentration of monomers as a function of time, right? What we're interested in is what is the size of our polymers, right, as a function of time, okay? And so we're going to find the fraction of monomers P that have reacted at time T, right? So we're trying to figure out, okay, P here is the number of monomers that have reacted. So P is sort of related with like the concentration of A minus concentration of A naught, if you will, right? The number of monomers that have reacted after some point in time, okay? And so it's, A minus A naught, right? So here we're asking for the percent that have reacted, not the percent left, right? So that's why it should be, I guess, like this, right? So the percent that have reacted is the initial concentration minus the current concentration divided by the initial amount. That gives you kind of that percent change, right? You multiply by 100, it's an actual percentage, but otherwise it's a fractional change, right? So you plug in what the concentration of A is as a function of time, and you get this expression here, right? And so that expression, right, on the previous slide gives us kind of how this, what fraction of monomers are left as a function of time, right? Now, if we want to ask the question about the degree of polymerization, right, again, what's the average size of the polymers, right? How many monomers make up the average polymer as a function of time, right? We'll use some information, right? The first thing we know, right, after two monomers react, there's now only one sort of active monomer left, if you will, right? When A plus A happens, right, to form A2, right here, there's each A has sort of a reactive site, if you will, right? A2 here has just one reactive site, right? So each reaction reduces the number of monomers by one, right? So each time a monomer reacts with another monomer or a polymer chain, the number of monomers available to react gets reduced by one, okay, right? And again, the same is true whether or not a monomer reacts with another monomer or a monomer reacts with a polymer, right? So if some polymer composed of N monomers reacts with the monomer A, right, you get a polymer of N plus one monomers, right? And it then reduces the number of active monomers by just one, okay? And so, right, based off of this, right, the average number of monomers in a polymer is related with that initial concentration of reactive monomers divided by the number of reactive monomers left. Okay, so again, that's sort of the average. Right, there can be polymers of larger length and of shorter length, right? But the average is as follows, right? The average is, this is your initial concentration, right, of reactive monomers, right? And this is your current concentration, right? And so on average, right, that concentration of active monomers that's lost is gone into creating some larger polymer chain, right? So the average size of the polymer chain, right, you're assuming, right, the average size of the polymer chain is related with basically, I've lost 10 monomers, right? If I've formed 5 chains, on average, each chain is worth 2 monomers in length, right? That's sort of the idea. Okay. And so using that average polymer length, okay, and plugging in for what we know for the concentration of A, the average length of a polymer has this functional dependence in time, or is also related with the fraction of polymerization by this equation here. So plugging in for what P is in terms of the time dependence. Okay, you get that equation there, right? So we look, for example, that fraction of polymerization, okay, versus average polymer length, right? That has this 1 over x type figure, right? Where the average polymer length is relatively short while most monomers live, right? Because again, this stepwise polymerization is any monomer can react with another monomer. So initially, you're just forming hundreds of like length 2, length 3 chains, right? You only start to get to much longer chain lengths once you've used up most of the lone monomers, and now what you're reacting is polymer-polymer reactions, right? So now, when that fraction polymerization starts decreasing significantly, right, that length of your polymer increases much greater, right? Because initially you're reacting 1 with 1 to form 2, or 2 to 2 to form 4, right? Later on, you're starting to react 8 with 8 to form length 16, right? So the size is doubling and doubling and doubling, right? And that thing grows, almost exponentially, right? When you get to much fewer active sites, right?